Hello, everyone. Welcome to Group Seven's video presentation. And in this presentation, we're going to go over the DevOps book of Chapter 13, Architect for Low Risk Releases. Now, one of the biggest challenges that companies with architecture of software development, one of their greatest challenges is whenever something more new or advanced is created, and in order to keep up with the demands, they would sometimes have to migrate to a more suitable architecture that addresses their current problems and organizational needs. And Jez Humble observed this phenomenon, saying that architecture of any successful product or organization will necessarily evolve over its life cycle. Like all everything on this planet, it evolves and it changes in order to adapt and survive. Now, Randy Shoup, who once was a chief's engineer at eBay before he moved to Google, he noticed these sort of patterns as well, and then he said that if they had tried to implement the 1995's equivalent of the microservices out of the gate, they would have likely failed, collapsing the entire system and most likely taking the entire company out of business. Now, one of the biggest challenges in migrating is uh, to make sure not to keep the system over tight in a monolithic structure. Otherwise, you would be you're sort of isolating yourself or the company's self uh, from the entire world that it's trying to access. One of the biggest consequences of these overly tight architectures is that because it's tightly coupled and then like the code is very strict and very limited of modifications, this could be a huge risk in creating global failures, which means that any developer trying to change it will most likely ruin it, and they would have a fear of not even attempting to change it themselves. Which, without these changes and these failures, that would also cause deployments to be very problematic. And then with these errors coming up, like these things could take days or even weeks in order to find and fix. And in an architectural um, perspective, it creates a downward spiral, which is a consequence of the second law of architectural thermodynamics, meaning that if the modifications are restricted to the point where even like a Jenga block, if you take one block out of it and then the whole thing would collapse, then it's not well structured out. So, in order to combat this downward spiral, uh, you would need to change any sort of tightly coupled architecture into a more loosely coupled architecture that has well-defined interfaces, and this helps improve productivity and better performance overall. And this sort of architecture also enables small productive teams to make small changes that can be safely and independently deployed without the need of changing the entire system per se. Um, One of these examples is Google's Cloud Data Store, which is one of the largest NoSQL services in the world. It is one of the largest services that Google has, yet it is only run by 8 people. That's it. It doesn't require any more than that, and and it has been very successful. So much so that like even Amazon and Google, with their tens of thousands of employees and developers, like with so much of a workforce, they still allow small teams to work on smaller and simpler units of development. And in doing so, this creates a more healthier flexibility and scalability of the company.
Okay, moving on to the monolithic versus microservices. At some point in their history, most DevOps organizations were hobbled by tightly coupled monolithic architectures that, while extremely successful at helping them achieve product or market fit, put them at risk of organizational failure once they had to operate at scale. Some examples were eBay's C++ application in 2001 or Amazon's Obidos application in 2001. Monolithic architectures are not inherently bad. In fact, they are often the best choice when it comes to the early stages of a product lifecycle. The functionality of a service will eventually evolve over time, so that means that our architectural needs should also change. Things that work at the starting phase may often crumble when the scale is increased by 10 or 100. There are 3 versions we should focus on. The first is monolithic version 1, or all functionality in one application. The pros are it's simple at first, there are low inter-process latencies, a single code base, and one deployment unit. And they also are resource efficient at small scales. The cons: coordination overhead increases as the team grows, poor scaling, and long build times. The second is monolithic version 2, or sets of monolithic tiers: front-end presentation, application server, and database layer. The pros: simple at first, a single schema deployment, and resource efficient at small scales. Some cons: poor scaling and redundancy, a difficulty to tune properly, and the all or nothing schema management. And then third, microservice, or the modular independent graph versus graph relationship versus tiers, and isolated persistence. The pros are each unit is simple, independent scaling and performance. There's also independent testing and deployments. Some cons: it involves a lot of cooperation, requires sophisticated tooling and dependency, and also network latencies. Keep in mind that monolithic supports startups while microservice caters to large teams with independent responsibilities to the customer. Um, moving on to the Strangler method for safely evolving architecture. The term Strangler application was coined by Martin Fowler in 2004 after he was inspired by seeing a massive strangler vines during a trip to Australia. He wrote, "They seed in the upper branches of a fig tree and gradually work their way down the tree until they root in the soil. Over many years, they grow into fantastic and beautiful shapes, meanwhile strangling and killing the tree that was their host. If we decide that our current architecture is too tightly coupled, we can begin decoupling parts of the functionality from our existing architecture. In this way, we enable teams supporting the decoupled functionality to independently develop, test, and deploy their code into production with autonomy and safety." The Strangler application involves placing existing functionality behind an API where it remains unchanged and implementing new functionality using our desired architecture, making calls to the old system when necessary. When we implement Strangler applications, we seek to access all services through versioned APIs, also called version services or immutable services. Versioned APIs enable us to modify the service without impacting the callers, which allows the system to be more loosely coupled. If we need to modify the arguments, we create a new API version and migrate teams who depend on our service to the new version. By repeatedly decoupling functionality from our existing tightly coupled systems, we move our work into a scale and vibrant, a safe and vibrant ecosystem where developers can be far more productive, resulting in the legacy application shrinking in functionality. Eventually, the goal is to possibly have the legacy application disappear entirely. As with any transformation, we seek to create quick wins and deliver early incremental value before continuing to iterate.
So next we're going to take a look at a case study involving a company called Blackboard Incorporated. Blackboard Incorporated is a pioneer of providing technology for the purpose of being used in an educational institution. In 2011, their flagship product was being bogged down by a legacy J2EE codebase that dated back to 1997. As they realized that the old system was leading to a more complex and error-prone system with the building, integrating, and testing, they realized that getting feedback from integration process required between 24 and 36 hours. As time went on, the amount of code commits decreased considerably from 2009 to 2010. What this showed them is that the difficulty was increasing towards introducing code changes into the code base. In 2012, there was a new focus placed on the implementation of code re-architecturing using the Strangler pattern. They accomplished this by creating what was known as building blocks internally that decoupled modules from the monolithic code base and made accessible through fixed APIs. One of the immediate effects was the decreasing of the monolithic source code repository size after they switched to the building block system. This was because developers are moving their code into their building blocks repositories. This allowed the developers to be much more productive. The conclusion of the case study by the head of the restructuring project declared that by moving to the building block system, code modularity increased drastically, which allowed the developers more independence and freedom. They also got much faster and better feedback, which would result in better quality. So then on to this chapter's conclusion. We learned in this chapter about how much impact the architecture we're working in can dictate how we test and deploy the code. In the Puppet Labs 2015 report, this was validated by showing the productivity of engineers in the different architectures. We must be able to safely migrate from one architecture to another. This is because different architectures are better for different goals that were set at the different time periods that we were using them. The techniques discussed, like the Strangler pattern, can help us migrate between architectures incrementally, which helps us to adapt to the needs of the organization that we are in. Yeah, thanks for watching.